All right, everyone, we are back, and I went and got a sweater because it is absolutely freezing up here. That's fine. All right, and this is actually the second time I'm recording this video because, yeah, I finished the last one and processed it and started recording this one, and when I was editing it, I realized that share screen wasn't working, so it was just me talking. And since you need to actually see the tables and everything, let's try this again. All right. Okay. So we talked about, let's go back up here, talked about all of these in the last video, right? So every truth functional statement is going to fall into one of these categories. They'll either be logically necessary or self-contradictory or logically contingent, right? Now, but when we are comparing two or more truth functional statements to each other, we have a different set of categories for the comparison. Okay, so the first one is logical equivalence. So say that two statements are logically equivalent means that they're going to have identical truth values under every possible truth evaluation. Okay, now what that looks like when you're comparing the truth tables is under the main operator, the truth values are going to be identical under all possible evaluations. All right, so if under one, um, the main operator of one formula, you have true, false, true, true, and then under one you're comparing it to, you have true, false, true, true. That would mean that those two statements are logically equivalent, okay? So let's go back over to um, the other page that actually has the tables, all right? So if we go back to this formula here, which was a contingent formula, look what we have here. So the main operator of this formula is this tilde, and the main operator of this formula is the dot. Well, under the tilde, we have true, or I'm sorry, we have false, true, false, false, and then over here we have false, true, false, false. Okay? Now, and this entire formula is represented by this wedge, but under the wedge we have false, true, false, false. Okay, so what does that tell us? That tells us that this formula, it's not the case that if T then B, that's actually logically equivalent to T and not B. Okay, now, and anytime you either disjoin or conjoin, so if this were a dot, it would work the exact same way. All right, so anytime you disjoin or conjoin one logically equivalent formula to another logically equivalent formula, that whole thing, the complex formula, is going to be logically equivalent to both of those formulas, okay? And we can actually show why this is the case, all right? So let me just copy and paste this really quick, all right? So it's not the case that if T then B is actually logically equivalent. Oops, got to change this to Times New Roman or something other than symbol. All right, is actually logically equivalent to either not T or B. Okay, so if you think about, again, the truth values of the conditional is true either when the antecedent is false or the consequent is true, which is exactly what this is. So if T then B is logically equivalent to either not T or B. Okay, now, but furthermore, if we distribute this negation inside of the parentheses, so we want to take this tilde, which is outside parentheses, and we want to distribute it within parentheses. All right, so since we're negating a wedge, okay, if we distribute this tilde, the wedge is going to turn into a dot. So anytime you distribute a tilde in front of a wedge, or you got to change the wedge to a conjunct, and if you're distributing it in a conjunct, you got to change the conjunct to a wedge. This is a rule known as De Morgan's rule, okay? So we would end up with this. So we change the wedge to a dot, a conjunct, and then we put a tilde in front of not T, and then a tilde in front of B, okay? Now, but then furthermore, whoops, let's back this up here. Furthermore, not T is just equivalent logically to T. Okay, so what that means is it's not the case that if T then B is logically equivalent to T and not B, right? So what we end up with here is either T and not B or T and not B, which is reducible to just T and not B. Okay, so this is actually a tautology. So disjoining one formula to itself is a tautology. Conjoining one formula to itself is a tautology. Okay, so all of these statements are logically equivalent then. Okay, so T and not B is logically equivalent to, it's not the case that if T then B, okay? And it's not the case that if T then B or T and not B is logically equivalent to, right? Is logically equivalent to T and not B is logically equivalent to, it's not the case that if T is not B, okay? All right, okay. Now, but when we are comparing formulas, whoops, right? So we got logical equivalence. So under the main operator, you'll have identical truth values, okay? Now, next we have logical contradictions here. So a logical contradiction, if you're comparing formulas, you'll know that they're logically contradictory if they have the exact opposite truth values under the main operators. Okay, so remember what contradiction means. If two statements contradict, that means that the truth of one guarantees the falsity of the other, and the falsity of one guarantees the truth of the other. So with contradiction, not only is it the case that they can't both be true, if two statements contradict, it also means that they can't both be false. Okay, so if two statements are contradictory, the truth of one guarantees the falsity of the other, and the falsity of one guarantees the truth of the other. So what that looks like in a table is under the main operators, they will have the exact opposite truth values, right? Okay, next we have logical consistency. So two statements are logically consistent if there's at least one truth evaluation where they both come out true. Now, what that looks like in a table is you will have at least one corresponding line. You will have at least one corresponding line where they're both true. Now, so if you've got one formula true on line 2, and then, in the other formula you've got true on line 7, these are not corresponding lines. Why? Because on line 2, you're going to have different truth evaluations than what you have on line 7. So the fact that one is true on line 2 and the other one is true on line 7, that doesn't mean that you have corresponding truth values. In order for them to have corresponding truth values, they have to be true on the same line. So if there's at least one line where they're both true and it's a corresponding line, they're both true on line 2 or 3 or 4, how many lines you have in the table, then you've got logically consistent statements. Okay, logical inconsistency is just when there is not at least one truth evaluation where the statements are true. Okay, now, but bear in mind here, like we talked about before, that inconsistency is different from contradiction. All right. So to say that two statements are logically inconsistent just means that they can't both be true under the same set of circumstances. Now, but that leaves open the possibility of them both being false. So all contradictions are inconsistent, but not all inconsistencies are contradictions. So if you look at the table and there's not at least one line where they're both true, but there is at least one line where they are both false, that means that you've got inconsistent statements that don't contradict. Okay, and if you want to think about this in terms of categorical logic, bear in mind that an A statement, the universal affirmative, all SRP, and the E statement, the universal negative, no SRP, they are contraries. They don't contradict each other. So they can't both be true, but they can both be false. So contrary statements are inconsistent with each other, but contrary statements are not contradictory, right? Okay, now, and you can have comparisons that fall into more than one, you can have formulas that fall into more than one category here. Okay, so if you've got two logically necessary statements, meaning that they're true under every evaluation. So not only are all necessary statements logically equivalent to each other, right? So if I've got two statements where they're true under every evaluation, well, that means that these two necessary truths are logically equivalent. Logically necessary statements are logically equivalent to each other, but they're also logically consistent with each other. All right. So if two statements are logically necessary, that means that they're both logically equivalent to each other, but they're also both logically consistent with each other. Okay, now self-contradictory statements. All right, if I've got two self-contradictory statements, they're going to be logically equivalent. So all contradictions are logically equivalent. Why? Because every self-contradiction is necessarily false. So if there's no possible circumstance in which contradictions can be true, at least in the systems of logic we're using here, so if I've got all zeros under the main operator of one formula, and I've got all zeros under the main operator of another formula, these are logically equivalent statements, but they are also logically inconsistent with each other. So all self-contradictions are logically equivalent, but also logically inconsistent. Okay, now, and then with contingent statements, contingent statements can be logically equivalent to each other. Contingent statements can be contradictory. Contingent statements can be consistent. Contingent statements can be inconsistent. It all just depends on what the actual truth evaluations are here. All right. Okay, so let me go back here and make sure I'm sharing the right screen, because that's why I screwed up the first time I tried to record this video. I didn't switch back and forth screen sharing. All right. And let's go ahead and compare these two formulas here. So formula one, we've got either R or if M, then not Q. And we have either R and M or R and Q. So either R or if M, then not Q, and we're comparing R and M or R and Q. Okay, now we've got three letter types here, so that's why we need 8 lines in the table. But what if this were the case? What if over here we had just if M, then not? So pretend that R is not even there. So we'll get rid of this R and we'll get rid of this R right here. And we'll also get rid of the wedge. Okay, would I only need 4 lines in my table over here, or would I need 8? I would actually need 8, and here's why. I'm comparing these two statements. Okay, so if I were just doing a truth table on this statement on its own, I could do that with just 4 lines. Now, but since I'm comparing statements, I need to make sure that my truth tables have the same number of lines. So since I need 8 lines over here, I need 8 lines over here as well. So even if all your letters aren't being used in both formulas. So here I'm using R, M, and Q. Here I'm only using M and Q. You still need to have the same number of lines in both of your tables when you're comparing formulas. Okay, so let's go ahead and get that back here. All right. Okay, so I've got 8 lines in the table. So to determine the number of consecutive ones and zeros under R, I take 8 and divide by 2, and that gives me 4. So 4 ones and 4 zeros under R. Okay, now, and I'm just going to go ahead and fill in those values over here as well. So 4 ones and 4 zeros under this R as well. Okay, now, and I've also got, again, if you just want to use this sidebar here, feel free to do so, but I'm going to go ahead and fill in all of these other values as well. Okay, and I've got 2 R's over here. So 4 ones and 4 zeros under this R, and then 4 ones and 4 zeros under this R as well. Okay, my next letter is M. So I take the number of ones and zeros under R, which is 4, and divide that by 2. So 4 divided by 2 is 2. So 2 ones and 2 zeros under M. Okay, and then we'll go ahead and put 2 1s and 2 zeros under this M, and 2 1s and 2 zeros over here. Okay, so that's all the M's. All right, and then my last letter is Q. So 2 1s and 2 zeros under M, take 2 and divide it by 2 again, and you get 1. And since Q is the last letter, you'll always have 1 1 and 1 0 consecutively all the way down all 8 lines of your table. Okay, and then I've got this Q over here. So 1 1 and 1 0 all the way down. Okay. Now, when it comes to operations here, what do we have? So we've got a negated Q here, so that is what we will have to do next. But as far as main operators go, this horseshoe is bound by 2 sets of parentheses, and the wedge is only bound by 1. So this is actually the main operator of this formula. All right, likewise, this dot is bound by 2 sets of parentheses. This dot, this conjunct, is bound by 2 sets of parentheses. Okay, and this wedge is only bound by 1. So that means that this wedge is our main operator over here. So to determine whether these statements are consistent, inconsistent, contradictory, or equivalent, we're going to compare the column for this wedge right here with the column with this wedge right here. Okay, now again, with this negated Q, you can fill in the value of Q and then fill in the value of the tilde, but you can also just fill in the value of the tilde. So since Q is true, false, all the way down the table, not Q is just going to be the opposite. So false, true, false, true, false, true, false, true. Okay. Oh, I forgot to fill in Q over here, so let me do that as well. Just to make sure we've got nice clean tables here. All right, so to find the value of the horseshoe, we're comparing M with the tilde, all right? And keep in mind the shortcut. So a conditional statement is false just in case the antecedent is true and the consequent is false. So in all other circumstances, the conditional is going to be true. Okay, so I've got true antecedent, false consequent on line 1. And I've also got true antecedent, false consequent on line 5. All right. So if M the not Q is false on line 1 of the table, it's also false on line 5 of the table. And then on every other line, it is going to be true. Okay. Now, and then the shortcut for the wedge. So to find the value of the wedge, I'm comparing R with the horseshoe. All right, so compare R with the horseshoe column. And the shortcut for the wedge is that there's only one condition where a disjunctive statement is false, and that's when both parts are false. Okay, and that only occurs on line 5 of the table. Okay, so on line 5 of the table, the wedge is false because R is false, and if M the not Q is false. All right. So that means on every other line of this table, the wedge is going to be true. So there's only one condition where this formula is false. All right. And the one condition where this formula is false is when R is false, M is true, and Q is true. In all other circumstances, this formula is going to be true. Okay, let's go over here. So to find the value of this wedge, we're comparing this dot with this dot. We're comparing these two conjuncts. Okay, so the shortcut for the conjunct is a conjunct is only true when both parts are true. So that occurs on line 1 and 2, and that's it. So in all other circumstances, this dot is going to be false. Okay, over here, I've got R is true and Q is true on line 1, and R is Q is true on line 3, and then this will be false on every other line. All right. Okay, so again, to find the value of the wedge, I'm looking at this column, this conjunct column, and this conjunct column. So here I've got that R and M is true, and R and Q is true. So that would mean either one of them are true. Right here I've got true, false, so that is true. Here I've got false, true, so that is true. And then on every other line, R and M and R and Q are both false. So on lines 3, 4, 5, or I'm sorry, 4, 5, 6, 7, and 8, not, so it's true on line 3. So on line 4, 5, 6, 7, and 8, this wedge is going to be false. Okay, now, and then when I compare the two formulas, I notice that they're both false on line 5. There's 3 lines where they're both true, lines 1, 2, and 3. So they're not opposite each other. They're not equivalent to each other, but there's at least one line in the table where they are both true. So that means that these are, whoops, these are logically consistent. I was going to type in logically, but I think it'll screw up the formatting. So these two formulas are logically consistent with each other. They are both true anytime R, M, and Q are all true. They're both true when R is true, M is true, Q is false, and they're both true when R is true, M is false, and Q is true. In all other evaluations, these formulas are not going to be necessarily consistent with each other, okay? So they're only both true in those 3 circumstances. But since there's at least one circumstance where they are both true, they're both, they're consistent with each other, okay? All right. So yeah, for the second time around, I hope I didn't seem too grumpy that I had to record this video over again. And hopefully when I edit it, I noticed that the screen sharing actually worked. If not, I'm gonna have to do it a 3rd time, and then I will be very, very, very grumpy. All right, okay, so the next video, which we'll get into next week, we'll be going over the indirect truth table method for determining whether arguments are valid or invalid, right? And it's a shortcut method. I know we all like shortcuts, and this is a particularly useful shortcut method, all right? Okay, I will see you all then. Thanks.